I have now a neural network implemented, a class with one single method called feedForward. The neural network gets a specific amount of input values, goes through a few layers of perceptrons, and at the end it returns with some output values. If I want to apply this to the green light capsules, there are a few questions might be raised, like what should be the input values of that neural network? How should I handle the outputs that come out on the other end? How many perceptrons do I need in the hidden layer? Do I need to change the activation function to a more complex one, or the unit step will be enough? In the next 1 or 2 videos, I will deal with issues like these. Let me try to answer the questions I just asked and talk about how I plan to apply the neural network. The capsules need to receive some information about their environment, which in this case is the track. What they should receive about it, that's not like set in stone. What I will do is that I will give them 5 sensors. Those sensors will be looking in 5 different directions and return with the distance of the wall towards the direction they are looking at. Those 5 values will then serve as the 5 input values of the capsule's own neural network. Those values go through the feedForward algorithm, and then I will get 4 output values from 4 perceptrons on the output layer. And since I'm using the unit step as activation function, that means that all those output values will be either 1 or -1. Now each of these 4 output values will be bound to one of the arrow keys. And if the output value is 1, the key will be pressed. If it's -1, it won't be pressed. That would be the idea. So I would have 5 input values and 4 units on the output layer. What about the hidden layer? The thing is that there is no general way to calculate an optimal size of the hidden layer. A hint I found online was that the size would be usually between the input and output layer size, which makes it in this case either 4 or 5. I will go with 5, but 4 really doesn't seem to make a huge difference. About the activation function, I will leave the unit step for now, but I will later show a few other ones like sigmoid or rectified linear unit. They all can be implemented in one single line, so no need to worry about them. Let's start this with creating a neural network in the game template. The arguments will be 5, 5, and 4, and then I call its feedForward method. That's what I did in the browser's console in the last video. The input values are now all set to 1 in the constructor. That needs to change because I will need to set those values in every iteration when I start the simulation. So I will write a new method in the neural network class called setInputValues that will get an array of values, and it checks first if the length of that array is the same as the size of the input layer, and if it is, then it fills the input values property with the elements of the incoming array. Okay, and I can use then this method before the feedForward in the game template. Set input values to 1, 2, 3, 4, 5. The length needs to be 5. And console.log the return value of the feedForward method, just so that I can check the console in the browser if I get any error or if I get 4 1s and -1s, as I would expect. And so far so good. Now I can leave this neural network for a while and I go and create a new smart cups, but this will be one I control myself with the arrow keys. That's for testing purposes because I will implement the sensors now and I want to make sure that those 5 values look okay. First of all, I simply want to have a capsule on the canvas and move it myself, so I create a new smart cups, a player, and use that object as the user inputs argument. So yeah, that's the capsule moving there. What it needs now is some sensors. The sensors will be properties in the smart cups class, and for each of the sensors I would need their starting point, which will always be the current position of the capsule's head, a direction as a unit vector, that's where they are looking towards to find the next wall, a line that will connect the starting point with the point where the sensor is intersecting with a wall, and the distance, its value will be the length of that line. What I already do have in the physics engine implemented, and I don't need to do it, that's a function that can find the intersection between 2 line segments. So here it is. It's called line segment intersection, and it does what's written here. It takes 2 endpoints of 2 line segments and returns with the intersection vector, or false if there is no intersection. So if I take a wall as a line segment and a sensor line as another line segment, put their endpoints in this function, then it returns either with a vector, then I will know that that's the point where they intersect, or false. So what I can do is I can check for every single wall on the track if it's intersecting with the sensor's line segment, and from the ones that do intersect, I pick the closest one, meaning the one with which the sensor's line segment's length is the smallest. That length value, that will be the number I will need for the neural network. I add a new property to the SmartCaps class, the sensors, and this will be an object. It will have a starting point, initialized as a vector, a distance, which will be the input value itself. For the neural network, I set it to 200 in default so that it won't look for walls any further than that. An array of directions, which will be an array of unit vectors. The size of this array is supposed to be equal to the size of the neural network's input layer. And finally, I will have a line. A line object is also from the physics engine. Its main job is that it needs to be displayed on the canvas. And I also set its color to gray after creating it. And here comes the getSensorData method, which will get an array of walls. Those walls will be, of course, the walls the track is built of. And this method has to find the distance values and display the line objects. First, I set the starting point of the sensors to the capsule's first component's position. That is the middle of their head. That's where the distances will be measured from. And that point will be the starting point of the line as well. Then I need to define the directions. The first direction is easy. It will just point ahead. I can get the vector pointing from the capsule's back circle towards the front circle and make it a unit vector. The next two directions will be simply the normal vectors of the first one. Since normal vector is already a unit vector, I don't have to call the unit method on them. So first the normal vector of the first vector, and then the normal of the second vector. Double normal means opposite direction. Now the last two directions are a little bit trickier. If I take the first unit vector, the one that's pointing ahead, and the second one, the one that's perpendicular to that, and add them together, then the result vector's direction will be halfway between those two, like 45 degrees in between. I only need to make it a unit vector. And if I do the same to the other direction, then I get the fifth unit vector as well. After that, I can iterate through those directions to find the closest wall for each one. I define the closest point, 200 pixels away from the starting point in one specific direction. If there is no wall closer than that, then the value will remain 200 at the end. That's what I set as default value for the distance variable. And then, for each of the walls that arrived in the wall array, I want to find the intersection with the current line. If there is an intersection, the line segment intersection method returns with its vector. And if that happens, if its return value is not false, and in addition to that, the intersection is closer to the starting point than the closest point at the moment, then that intersection vector will become the closest point. Yeah, and at the end of the iteration, I can display that closest point as a green circle and set the line's endpoint to that point, and then finally draw that line. And that would be all I need to find the 5 distances. All I do is call this method on the top of the game logic. The argument will be the race walls. And then if I go to the browser, I should see 5 lines and 5 green circles at the end of those lines. Yeah, the lines are not displayed for some reason, but luckily the green circles are there, and they even seem to be properly placed. So my overall impression is more on the positive side. Let me just work on this displaying issue a little bit. Yeah, so the lines are not displayed because I didn't call the draw method here after setting up the sensor's line. And let's do that if there is an intersection found between the line and the wall. The line turns into red, otherwise it stays gray. So here I set it to red. And to see what those 5 distance values are, I display them on the canvas with the fillText method. The magnitude of the vectors that point from the starting point to the closest points, and that rounded to 4 decimals. And those values go below each other. And let's see how the canvas looks like after this. Yeah, so those 5 values keep changing based on the position of the capsule's head compared to the closest walls in specific directions. And in every iteration, those values will be the input values of the neural network, and the output will be also changing based on the calculations inside of the neural network. And if all the weights and all the biases are set in a specific way, the capsule will know when to press which arrow key in order to drive around the track. Now, calculating those weight and bias values to get that result, that's not a task for average humans. The best I could do on my own would be randomly guessing them and hope that one day the capsule happens to drive a full circle by itself. But doesn't that feel a little bit similar somehow? Haven't been in a situation like this before a few episodes ago? So let's say there is a problem and there is an ideal solution of a problem, and we try to come up with various ideas that could serve as a possible solution for that problem. Right, yes. It's time to apply the genetic algorithm on neural networks. This is something that belongs to the so-called neuroevolution, and that's what will happen in the next video.